So, what we have here is we have points A and B lie on the curve of g of x between 0 and 3. Point A is the only point of inflection. Okay, so what that means is before point A we can see it's concave up, and after point A we can see that it's concave down. Okay, it's concave down after point A. Which of the following statements is true? Justify your answer. So we've got g dash of 1 is less than g dash of 2. So now g dash, what that means is the slope. So we're talking about the slope at x is 1 is less than the slope at x is 2. We have the slope at x is 1 is equal to the slope at x is 2, or the slope at x is 1 is greater than the slope at x is 2. Now you can tell just by looking at it. Okay, you can tell just by looking at it that it is steeper at A than it is at B. All right, if you consider the tangent drawn there compared to the tangent drawn here. We also know that point of inflection corresponds with the steepest point over a given constraint. Okay, so that's where it's going to be steepest, and then it starts getting shallower and shallower and shallower. Okay, so that has the greatest rate of change there at g dash of 1. So we're going to tick the third box. Okay, the slope at x is 1 is larger than the slope at x is 2, and so we get 1 mark for the checking the right box. And then as far as the justification goes, we're just going to say something like it is steeper at x is 1 than at x is 2, or you can refer to the point of inflection occurring at A, which means that's where the slope is maximized. Okay. All right, on to the second one. Now, the couple that I marked misread this, because this is talking about the second derivative. Okay, the second derivative, and the second derivative reveals to you when it's concave up and when it's concave down. So, if the second derivative is negative, that means it's concave down. If the second derivative is positive, that means it's concave up. Now we know it's not going to be equal to 0 because that would suggest it's a point of inflection, and we're told there's only one point of inflection, so it's not the middle box there. All right. Now if we look at this interval, we can see at point B it is concave down. When x is 2, it is concave down, which means the second derivative is negative. So we're going to tick the first box, and our justification is going to be because the function's concave down, the second derivative has to be negative. Okay, that's question 2. All right, question 3. Anyone want to talk about this one? Very good. So we've seen this pop up in a few previous tests, I think. So you've observed this question before. That's from the 2017 exam, and they've included it in the 2020 sample. Okay, on to question 4. We've also talked about this one before. We've seen this pop up when we were talking about logarithmic functions. So the only thing I'll stress is, ln of x is defined for x is greater than 0. So we have 3x plus 8 being greater than or equal to 0. So we do it for a specific case. We have to draw a graph. And then we have the general case in terms of B and C. Now, anyone want me to go through any parts of this?
It's equal to as well.
Very good. Okay, on to question 5. Here we have a confidence interval for proportions. So I think just if I can talk about part A, explain the meaning of the confidence interval. It's easy to get tripped up when you're sort of justifying claims or explaining what a confidence interval shows. Okay, so this is a 95% confidence interval, and so it's performed by the government. They've made this confidence interval, and so remember, what it means is they're 95% confident the true proportion lies somewhere in this region. Okay, 95% confident the true proportion lies somewhere in that region. So that's what a confidence interval is a measure of how confident we are the region that the true proportion or true mean lies in. Okay, anyone want to go through any of these parts? Part B, 1 and 2, just one. What proportion of students in the sample always keep their cupboard locked? Okay, so this is generated using performed a sample, right? They sampled 320 junior secondary students, and we found this was the lower boundary and this is the upper boundary. And so we're asked, find the value of p hat. Okay, they're saying what's the value of p hat such that we generate that confidence interval? All right, so because it's the 95% confidence interval, so what we'll bring up is the lower boundary for the 95% confidence interval is, I'll bring it out. So p hat take 1.96. All right, so I'm going to probably describe this in a more complex way than it needs to be to begin with. P hat times 1 take p hat on top of n. Okay, so that's the lower boundary of the confidence interval, and we know that that is equal to 0.797, and we know that n is 320. So p hat, right, p hat is going to be x, that's the number of people that lock their lockers, divided by 320. Square root of p hat, so that's x on 320 times 1 take x on 320 on top of 320. So that's one way we can think about it, but that's a way more complex way of thinking about it. P hat is always going to lie exactly halfway between the upper and the lower boundary of the confidence interval. Okay, so p hat is basically the average of those two values. And I'll show you like why that's true in terms of the confidence interval. Like if you think about, here's the confidence interval, square root of that thingamajig there. Okay, if we add the lower boundary and the upper boundary together, we get, what are we going to get? We've got that part and that part are going to cancel, so we'll be left with 2p hat, all right, equals the lower boundary plus the upper boundary. So what's that? 0.797 plus 0.878. And then we can just find p hat by dividing both of them by 2. So that's probably the best way to think about it, the simplest way. All right, that's the same occurs for a sample mean as well. It's always going to lie between the lower, halfway between the lower boundary and the upper boundary of the confidence interval. Okay, so that's B part 1. What proportion of students always keep their cover blocked? And then, so that gives you the p value. And then in order to find, well, how many students, so we've got 320, and then multiplied by p hat, that's going to tell you how many keep their locker locked. Okay, any other parts in there? Okay, on to question 6. I would probably like to talk about this one, if people are happy to. All right, so firstly, I'm going to talk about sort of probably 3 parts to it. So we have, if y equals x e to the minus x, find dy of dx. So here we've got the product rule, we've got u dash, v, and v dash. So we'll smash all that together, u dash v, plus uv dash, it's going to become negative. All right, that's the first derivative. Okay, hence, all right, hence, that means using what you just did, show that the integral of x e to the minus x. So we're asked to find the integral of x e to the minus x. That's what we want to find. Okay, so this is integration via differentiation, and there's almost always an exam question that involves this, okay? Where you don't know how to integrate this, but we do know if you differentiate this function, this is what you obtain. Therefore, the integral of this function is equal to this function. Okay, so this is an integration statement that we've discovered by differentiation. All right, and so what to look out for? Differentiate this, hence integrate this. Okay, that means I need to make an integral statement. I've just observed, if I differentiate this function, this is what I obtain. Therefore, here's my integral statement. The integral of this has to equal this. And we are interested in only one part. We're interested in this component of it. Okay, we want to isolate that component. So we're going to split the integral up. So we have the integral of e to the minus x. Take the integral of x e to the minus x equals x e to the minus x. And now it's just an equation that we're solving through for this part. Okay? So first I'm going to subtract that component from both sides. So we'll have minus x e to the minus x equals x e to the minus x. Take away the integral of e to the minus x. So I've moved that part over here. I'm going to move the negative across as well. So I might just do that in one step here. I'm going to rub it out there and place it over here. All right, and now we're just going to evaluate that integral. So that part, we don't need to integrate that, that stays as it is. And the integral of e to the minus x is minus e to the minus x, and then plus c. And so that's what it asks us to show. All right, so there's 3 marks there. Got to make sure we get those ones. All right, then we have a graph and we do an overestimate and so forth. So I think we're okay doing those. New, calculate the new overestimate, that's okay. I just want to talk about probably part C with reference to A part 2. Okay, so that means you have to use what we've done in A part 2, and this is what we did in A part 2. Okay, so we have to use that. Find the area bound by the function, the x-axis, and the vertical lines x is 1 and x is 5. Okay, so what this means is find the integral from 1 to 5 of x e to the minus x. All right, now we know that the integral of x e to the minus x is this part here. That's what we've explored just before. We're referencing that part. Okay, you never do anything in vain, so we're going to use that now. So straight away, we can go straight to the definite integral. We know that if you integrate this, this is what it goes to. So we'll have, yeah, minus x e to the minus x, take e to the minus x from 1 to 5. All right, now we don't need the plus c because this time it's a definite integral. All right, and then we just put in the upper boundary. And then we take away the lower boundary. And there's a few things we can simplify here, but not much. All right, so we've got minus 5e to the minus 5, take e to the minus 5. These are like terms because they have the same base and the same power. So minus 5, take away one lot of it. That collects to minus 6e to the minus 5. And then we have take away this component. We've got, these are the same again, they're like terms. That'll collect to minus 2 lots of e to the minus 1. Now, that's perfectly acceptable there. You've got full marks there, although just how other ways it can be expressed. This is minus 6 on top of e to the 5 and plus 2 on top of e, right? So we can take the power to the bottom, negatives will become positive, and we've found the exact area there using the integration formula provided to us. Okay, so that's really the only one I wanted to talk about from those parts. Is there any other parts from that question anyone wanted to ask about the overestimate or underestimate? Very good. Okay, so that's the end of booklet 1. Now I printed this exam in 2 booklets just to show you when you rock up to your exam you'll get 2 booklets and you'll have a formula sheet. Okay, so let's go through to question booklet 2. Anyone want to go through question 7? This is a reasonably sort of common question that we've sort of picked up in continuous random variables. All right, so I'd expect us to be pretty okay with that. Question 8, this is quite a tricky question. Anyone want to go through any parts of question 8 or?
Wait, can we go through part, question 7, part C,
Absolutely. Question 7, C, part 2. Find the minimum sample size in order to calculate a 90% confidence interval with no more than 5 checks per day. So we're using n equals, and we've got an n formula. So it's not a proportion, it's a sample. So 2 times 1.9, it's not going to be 1.96, it's going to be a ZR from 2. That's not right? That's standard deviation, isn't it? 2 times 1.9 sigma on top of W squared. Okay, so there's two parts to this. Firstly, we're asked to do it for a 90% confidence interval. So that means we need the value of Z alpha on 2 for a 90% confidence interval. So the way we do that is this is an inverse normal for the Z distribution, and we're saying I want this to be 90% of the area for a Z distribution. What are these values? And you get minus 1.645 and 1.645. Okay, so everyone okay with that? All right, ask me if you're not sure. So we've got the value for Z alpha on 2. We know the standard deviation, we know the width, so we're just plugging all of those numbers in. And the standard deviation for this circumstance is based on the sample, assume sigma is
19.31.
19.31. And we have a width of 5. And we're just evaluating that. Anyway, this comes out to 161 or something like that. Is that right?
Yeah. Yep.
161.2. And so because we've calculated n, this is one of those circumstances where we always round up. Always round up when you're calculating n with this formula to guarantee that level. 162 students. Yeah, so there's probably 2 marks for that part, and then 2 marks for plugging it in, and then the like final mark from making sure you're rounding. It seems like a lot of marks.
Do you have to show that you're working out the finding or not? Just right.
You can just write it. Yep. All right. Okay, so we'll move on from that one. So yeah, does anyone want to talk about question 8 at all?
Maybe part B.
Yep, part B. Okay, yep, so let's go through this. This is the tricky part, really. So firstly, we've got to show that the second derivative is this. So what you need to do is you need to find the first derivative and then the second derivative, and then show that they're the same. Okay, so we've got h dash of x is e to the minus x, x to the n. So this is a product rule.
Is that dash function?
H of x. X n take 1. Good. Okay, so we get our first derivative. Okay, so that's the first derivative, all right? And now when we're going to find the second derivative, we already know what this part differentiates to because we've just done it, okay? The derivative of this part is this whole thing here. So we can say that this part goes to, and there's a negative out the front, so I'm just going to put a negative, and then the derivative of this part is this whole thing here. Like you can repeat the product rule if you want to, but we're going to end up with the same thing. Okay, so that part goes to that. And then we've got to do the derivative of this component. Okay, so this is the first derivative. For the second derivative, we know the derivative of that part is this here. And so now we need to find the derivative of this part. So we're focusing on the second part there, and we'll use the product rule again. We have u is n e to the minus x. Alright, so all I'm doing there is applying the power rule, right? X to the n take 1. The n take 1 comes down the front, n take 1, x to the power of n take 2. Alright, so we'll smash all those parts together. So we have plus, and then, so u dash v plus u dash. Alright, so we've found the second derivative. We're sort of 2 marks, and we just need to get that third mark by showing what we have here is the same as what they have up there. Now there's a couple of ways we can do that. We can attempt to factorize this, which isn't too bad, or we can even expand what they have and show that they're the same. That's a perfectly suitable way of doing it. You can take h dash dash of x and distribute that to show that they're the same. But looking along, we can start to see, the first thing we can see is that e to the minus x is common. We can even see some things are going to cancel. All right, so I'm looking at this. Let's distribute that negative first, and then we'll start factorizing. So we'll have e to the minus x, x to the n. Here we're going to have negative n e to the negative x, x to the n take 1. Negative n e to the negative x, x to the n take 1. N take 1, e to the negative x, x to the n take 2. Okay, so they're all the terms. We can see e to the minus x is common, so that's something we can pull out the front. The other thing I'm looking at is that these are actually the same term, repeated, okay? They're exactly the same. They have the exact same base, the exact same powers, so we can collect those to be 2 lots of n e to the negative x, x to the n take 1. So let's just do it in a couple of steps. Now, this last part, okay, I'm going to do this in a lot of detail, more detail than is necessary, just to show you how it's true. So first, let's factorize the e to the x. Okay, so you can see what we have is really starting to look pretty close to what they've got up there. The only other thing they've done is factorized x to the n take 2. So let's do that and explain why. If I have x to the n take 2 multiplied by x squared, okay, if we expand this, all right, we would add the powers together. Now, n take 2 plus 2 simplifies to x to the n. All right, and then we can just process across. The same applies. 2n to the x, n take 1, plus n take 1. And that's it. All right, so that's a perfectly suitable way of demonstrating it's true. So we sort of get 2 marks for getting the second derivative, and the third for showing the factorization. Collecting the like term showing the factorization.
Mr. Rose, what about the negative 2nx to the n take 1? That n take 1 would be?
Yeah, that should just be 2nx, shouldn't it? Oh, sorry, I didn't simplify that.
Yeah.
That's better. Yeah. So if you x to the n take 2 times x, okay, like at the moment, that's x to the power of 1. If you add those powers together, you'll get that term there. So yeah, that matches then. Yeah, good pickup. All right, so there's quite a lot of algebra involved there. And then for the second part, hence show that it always has 2 distinct points of inflection. Okay, so here's another hence. And even if you haven't got those 3 marks, you can still get some marks here using the formula that they provide you with. So this will probably be the last one I'll just talk about quickly before we break for recess. So we have e to the minus x multiplied by x to the n take 2, x squared take 2nx plus n take 1. All right, cut that out. Okay, hence show that it always has 2 points of inflection. Well, points of inflection occur when the second derivative, which is this function, equals 0. Alright, so that's how we communicate it. Point of inflection when second derivative equals 0. So we're solving when this equation equals 0. Now the first thing we'll do, the first mark we get is for applying the null factor law. E to the minus x does not equal 0. X to the n take 2 does not equal 0 because x does not equal 0. Alright, so then we're just focusing on the quadratic component here. We have x squared, take 2nx plus n times n take 1. Okay, so that means this component equals 0, and we need to find what are the solutions to this component. Now you basically have two paths you can follow here. We can find the discriminant, okay? And remember, if the discriminant is positive, that means this has two solutions. B squared take 4ac. We can find the discriminant and show that it's positive, that it has two solutions. Or we can find the roots of this quadratic via factorization. So if we're going to find the roots, it looks a bit tricky to find them, right? Because we don't have numbers, but we're looking for two numbers that multiply together to give us n times n take 1. They're your numbers, okay? And when you add them together, you get 2n. Okay? So what it factorizes to is x take away n, x take away n take 1. All right? So we've found the roots, x is n, or x is n take 1. All right, so that's they're a tricky 3 marks to get though. This question here is sort of the equivalent of the conjecture question for this exam, because you're performing a proof about the nature of the graph with a general function rather than with a specific circumstance. All right, and I think question 9 there was pretty straightforward. And maybe when we come back, if people want to, we can talk about question 10, probably part D. That's a good question there. That's a good one to have a crack at. But I think most of question 10 is pretty straightforward. All right, guys, enjoy your recess, and I'll try to sort out this tutorial issue.
But Mr. Rose, did you want me to pause this?
Oh yeah, thanks, mate. Yeah, cheers.